scuba instructor since 1994. I have taught probably somewhere in the ballpark of about 3,000 people how to scuba dive. And I have about good job. I have about 5,000 total scuba dives in my logbook. So today what we are going to do is we're going to talk a little bit about math and how it pertains to scuba diving. The little bit that we need to know, it's pretty basic arithmetic, but there's a little bit that we need to know about scuba diving and how our body reacts to the water, the environment that we're in. So that's where we're going to start. If you guys have questions, shout them out as we go along.
The smart board. Jonathan, come here. Jonathan.
He responds to buddy. It's okay.
Jonathan.
Good job.
Uh-oh.
All right, first thing that we are going to talk about today is how pressure relates to our body. What happens when we are in the water scuba diving. So two things that we really need to worry about, and these are the main factors in scuba diving that we have to figure on every single dive that we do. All right? Good job.
Yay!
No, you're not. So the first thing we are going to do, stay there. So the two main things that we deal with are volume and density in the water, because that plays a big factor in the way that we scuba dive. These are the main things that we have to keep track of. So our first one all relates to our depth in the water that we're in. So it all relates to the depth of the water that we're in. For every 33 feet of water that we descend down into, we add an atmosphere of pressure to our body. At the surface, we have standard atmospheric pressure, which is 14.7 psi. So for every 33 feet, we add another atmosphere of pressure to our body. So at 33 feet, we have 2 atmospheres pressure. At 99 feet, we have 4 atmospheres of pressure. So on and so on and so on, as deep as you want to calculate it. Why is this important to us? The reason we have to keep track of this when we scuba dive is we have to figure out how much of the air that we are breathing, number one, how much we are going to use, and number two, how much nitrogen our body is going to store. All right? So, for an example, let's say we take a balloon full of air. Even in a swimming pool, take a balloon full of air, we fill it with a certain amount of air, it doesn't matter how much it is. We tie it off and we take it to the bottom of the swimming pool. What's going to happen to that balloon as we go down? That's exactly right, it's going to get smaller. So that balloon is going to get smaller as we go down in the water, but we don't lose any of the air. It's not escaping. What happens to it is that air becomes compressed. So it gets smaller in size. Well, what happens inside that balloon is we still have the same number of air molecules inside that balloon, but now because that air space is smaller, it's more compressed, those air molecules are pressed closer together. So the air becomes more dense. Why this is important is, number one, this affects our air supply that we can breathe. So if we have an air supply on the surface that is full, and we take that down to 99 feet, or 4 atmospheres, we now have 1/4 of that air supply that we had at the surface. So on a scuba dive, this very plainly means that at the surface, a scuba tank that would last, say, 60 minutes on the surface, when we get down to 99 feet, is now going to only last 1/4 of that time, or we're only going to get 15 minutes out of that scuba tank. So number one, that's why it's important to know this equation. And we can calculate this as deep as you want to go. 1/5, 1/6, 1/7, 1/8, as deep as we want to go. Recreational scuba diving is good to 132 feet. That's our limit in recreational scuba diving. Technical diving, you can go as deep as you want to go. The deepest recorded dive, which was done by the Navy, is in the area of 2,800 feet, somewhere in that ballpark. So, that's how our air supply is going to be affected. But why is the density of the air going to make a difference to us? And it's all because of what is in the air that we are breathing. There's two major components in the air that we're breathing, right? What? You're hungry? Go stand in the corner. So there's two major things in the air that we're breathing, which is oxygen and nitrogen. Okay, let's go stand. Good job. There's two major things in the air that we are breathing. Number one is oxygen, which comprises about 21% of the air that we are breathing. The other thing that we are breathing is nitrogen. So we have both of those factors, and there are some anomalies and some trace gases in there. But for the most part, it's 21% oxygen, 79% nitrogen is what we are breathing. So when we go deep into the water, our body metabolizes, just like it does on the surface, our body metabolizes that oxygen that's in the air that we're breathing. But it doesn't metabolize the nitrogen that's in there. All we're doing is we're storing nitrogen. So right now, here on the surface, we have a certain amount of nitrogen in our cells. And those nitrogen gases are just traveling around in our system like they do every day of the week. So what happens to those nitrogen bubbles in our system as we go down in the water? The same exact thing that would happen to that balloon in the pool. Those nitrogen bubbles get smaller and smaller and smaller. So, because all of those nitrogen bubbles within our cells are smaller, what happens is our body can store more nitrogen on board. So, all those nitrogen bubbles get smaller and smaller and smaller. As we inhale, we take more nitrogen into our system. It fills those cells back up with nitrogen. And again, we're at 100% of the nitrogen that our body can handle. Doesn't hurt us, has no effect to us in any way, shape, or form when we're underwater. The problem is if I get down to 99 feet and I stay down there for a certain amount of time, my body takes in more excessive nitrogen, and now I start to head back to the surface. What's going to happen to all those nitrogen bubbles in my system? All of those nitrogen bubbles are going to expand. So, all of my cells that are at 100% of the nitrogen they can handle are now going to be super exposed to nitrogen, or we're going to have excessive nitrogen in our system. So as we come back to the surface, those nitrogen bubbles expand more and more and more, and we have excessive nitrogen in our system. Now, every breath we take, every time we exhale, we get rid of excessive nitrogen in our system. So it really isn't that big of a problem to us. Let's say we went underwater, we stayed too long at a certain depth, and our body took in too much excessive nitrogen. What happens is then, as we get to the surface, those bubbles expand to their largest rate, still traveling around in your surface, you're still exhaling them every breath that we give. But if those nitrogen bubbles happen to hit an area where they block off blood flow to the nerves and to the tissues, this is called decompression sickness, or the bends. So this is our biggest problem in scuba diving, and this is why we keep track of what we do. So, the two things that we have to remember are our volume and our density of the air that we're breathing. As we descend, the density in the air increases, but the volume decreases. So if you can remember one, you can remember the other one. They're always the opposite of each other. As volume decreases, density increases. So we have to calculate before every single dive that we do how much excessive nitrogen we are going to have in our system.
Can I answer this?
Absolutely.
My question is, this is a kind of reference, how dangerous is this? I mean, it's not that, okay, I got just extra nitrogen in my body, so just start breathing faster. What's gonna happen to somebody if this happens? Why are we so worried about it that we have to?
So the biggest problem with decompression sickness is it blocks off blood flow to the nerves and to the tissues. So if you wake up in the morning and you've been sleeping on your arm all night and your arm is asleep, you can barely feel it, those are the symptoms of decompression sickness. So by cutting off the blood flow to those nerves and to those tissues, you're killing those nerves and tissues. Depending on where the decompression sickness lands, it's generally in the weakest points in your body, in joints where those bubbles can expand at their greatest rate. What can happen is if those nitrogen bubbles happen to land in your spine, decompression sickness can actually kill you without too much of a problem. So this is why it is very important that we keep track of it for every dive that we do. Now, the only treatment for decompression sickness is to be put into a recompression chamber. So a recompression chamber is just a chamber, and you've probably heard of these. It's just a chamber. They put you inside, close it off, they add air pressure to that chamber, and that simulates that it's taking you down in depth. And what happens when we go back down in depth? All those bubbles shrink down to a smaller size. Those bubbles that were blocking off blood flow to the nerves and to the tissues, now they start traveling around in your system again. It gives us a chance to exhale those every breath we take. Then what they will do is they will slowly bring you back up to the surface or slowly release the pressure in the chamber and let those bubbles expand very slowly. Then what happens is we off-gas those. When we exhale, it takes away all of the excessive nitrogen in our system. But the damage can already be done by the blood flow that was blocked off by the nitrogen bubbles. If you're in a recompression chamber, the average time you're in a recompression chamber is anywhere from 12 to 30 hours. So you will be in there for quite a long time. And again, this can be life-threatening. There have been numerous people around the world that have died from decompression sickness. So everybody is different. Everybody absorbs nitrogen or stores nitrogen at a different rate. So you could have two people on the exact same dive, the exact same profile. One person could get decompression sickness and the other person could not. So everybody's different for every single dive that you do in the water. So this is the main reason why we do it. So now I'm going to show you how to calculate how much excessive nitrogen is in your system. Questions? So this is a dive tank. This allows us to do two different things. This allows us to calculate how much residual nitrogen is in our system, and this also will tell us the maximum depth that we can go to. Now that doesn't mean that we're going to have enough air to stay down at that depth, but that means that's the maximum time we can go to at a specific depth. So on the very top of the chart we have our depth. Every 10 feet all the way across the board. So, we start at our depth. Pick any depth that we want to go to. Let's say we're going to go to 80 feet. If we follow 80 feet all the way down to the bottom, we see that we can stay at 80 feet for no longer than 30 minutes. That is the maximum amount of nitrogen that our body can handle, or the maximum amount of nitrogen we can store in our system safely. So after that 30 minutes, assuming we have enough air to stay at that depth for 30 minutes, after that 30 minutes, that doesn't mean we're going to get decompression sickness. That means your chances for decompression sickness are greatly enhanced after that time. So here, let's say we're going to go down for 25 minutes. We follow 80 feet down to 25 minutes for the next greater number, which here is 25 minutes. We follow that over until we get, keep touching the floor.
I know.
I follow that over until we get 25 minutes. We follow it over until we find a letter. Now what this letter does, that just tells us a hypothetical amount of nitrogen that's in our system. Just allows us to calculate how much it is. That's all we're doing with it. So right now we're an N diver. It means we have N amount of nitrogen in our system. What does that mean to us? It doesn't really mean anything. It's just the way to keep track of how much nitrogen is in our system. Table number 2 here tells us how long we're going to stay on the surface. So all the time that we spend on the surface allows us to get rid of excessive nitrogen in our system. Allows us to off-gas that nitrogen is what it does. So the more time we spend on the system, the more we get rid of that excessive nitrogen that is in our system, which means then on the second dive or on a third dive, we can spend more time in the water is what it comes down to. So we're an end diver. Let's say we are going to spend an hour on the surface. Follow N over until we find 1 hour within one of these boxes, which is 1 hour to 108. We follow that all the way down to the bottom, and that turns us into a D diver. The closer you are to ABC, the less nitrogen you have in your system. The closer you are to the bottom of the alphabet, the more nitrogen you have in your system. So we went from an N all the way down to a D diver. So, again, all this is doing is keeping track of how much nitrogen we have in our system so we don't go over our maximum limits that are in the water. Now that we know that we are a D diver, we start in the same spot on the chart in the back section. This is going to do 2 things for us. This is going to tell us how much residual nitrogen in minutes we have in our system, and it's going to tell us how deep we can go on this next dive. So we always go shallower on dives, second, third, fourth dive. We always go shallower than we did on the previous dive. So our first dive was to 80 feet. We can go back to 80 feet if we want, but we do not go any deeper on the second dive. So let's say on this dive we want to go back down to 80 feet. So we're a D diver. We're going to follow 80 over and cross it with D. We can see that we can stay only 19 minutes on the bottom because we still have some residual nitrogen left over in our system. We have to keep track of all the residual nitrogen from dive number 1, add it to the nitrogen we're going to get on dive number 2 to give us a total amount of nitrogen that's in our system. Again, that's all we're looking for. So we have 19 minutes worth of residual nitrogen in our system, or 19 minutes of total bottom time we can spend on this dive, and we have 11 minutes of residual nitrogen system in our system from dive number 1. Which means, very simply, if we spend 10 minutes on this dive, we can stay up to 19 minutes. We're only going to spend 10 minutes in the water on this dive. We still have to keep track of all the residual nitrogen from dive number 1. So we know that is 11 minutes worth of residual nitrogen. We stay on the bottom for 10 minutes on this dive. After this dive, even though we were only in the water for 10 minutes, our body's going to act like it has 21 minutes worth of nitrogen in it, because it does. 10 minutes from this dive, 11 minutes still left over from the previous dive. And then that's how we calculate how we stay in the water. At this point, we would go back to our first table. And we would do our dive, but for our recalculated nitrogen time. 80 feet, 21 minutes would then turn us into a K diver, and we do this scenario over and over and over again for as many dives as we want to do for the day. Does that make sense? So, this is very easy because we have a chart that we have to follow. This is very linear. All we do is follow the arrows. The arrows push us in the right direction. We keep track of the time. We actually take this in our logbook. We write this out for every single dive that we do to make sure that we are within the limits of the dive tables. So we don't want to get outside those limits because then again, it increases our chances of decompression sickness. So if we get decompression sickness, let's say we're diving locally, and we get decompression sickness, our closest recompression chamber is at Hennepin County Medical Center. So in Minneapolis, there is a recompression chamber that we could go to. So all is fine and well. We get to the recompression chamber, we go through our treatments, hopefully in the end we are okay. What happens if we are in the middle of the Caribbean and we get decompression sickness? There aren't very many chambers around the world. We're lucky that we have one here. So if we're halfway around the world and they don't yet have a recompression chamber anywhere, you could be in really serious trouble really fast. So this is why it's important to know this. This is why we do the math on every single dive that we do. Questions?
question I would have would be, if the nitrogen gas is a problem, why not take just pure oxygen?
Because pure oxygen is toxic to us. So we can't get over a certain percent of oxygen in our system. And the best example for this is, we need approximately 15% oxygen to stay conscious right now in the water. All right? Right now on the surface, if our oxygen level drops below 15%, we go unconscious, but you can't stay awake without that amount of oxygen in the water, in the air that we're breathing. So now what happens is, as we go deeper into the water, because that air is more dense and it packs more of those oxygen molecules in it, your body processes that oxygen so much more efficiently underwater. So, oxygen is actually a very toxic substance to us if you take it in high doses. Right now, at the atmosphere that we're breathing at, where we are normally, the normal amount of oxygen that we get into the air that we're breathing is perfectly fine to our body, the way that we metabolize it. But let's say we increase the efficiency of our metabolizing the oxygen by 300%, which is very easy to do when you go underwater. It can be very, very toxic to us. Oxygen toxicity can kill you almost instantaneously when you're underwater. Now, within a normal recreational scuba diving, 130 feet or 132 feet, we don't really have to worry about this. The air that's in your tank is the air that we're breathing right now. There's no difference to it. The only thing is that it's been cleaned of all impurities and it is 100% dry. There is no moisture in the air that you're breathing in any way, shape, or form when you're underwater. So, oxygen toxicity isn't that big of a deal to us, unless we were to increase the amount of oxygen in our tank by decreasing the amount of the nitrogen that's in it. Now, when we get into technical diving, anything below 132 feet, we can't go beyond about 200 feet. It's 220 feet. Anything beyond 220 feet with the air that we're breathing now becomes toxic to your system. So air is good to 220 feet and no deeper. Well, I've done several dives below 300 feet. So now we have to remove the oxygen out of the tank that we're breathing, otherwise it's going to become toxic to us. But the problem with that is if I drop the oxygen too low, what's going to happen when my body can't process that little amount of oxygen? You're going to go unconscious in the water, which is a very big problem. So technical diving is 100% math, because you have to figure down to the last molecule, literally, how much oxygen you have in your scuba tank, how much nitrogen you have in your scuba tank. Now, the one thing that nitrogen does with us in the water is the nitrogen has a narcotic effect to us when we're in the water, and this is called nitrogen narcosis. It starts generally at about 100 feet. What happens is you just become, it's like a mild intoxication is what it's like. So you get euphoria, you can get tunnel vision, you can get a whole bunch of these symptoms, and it just makes you act crazy. Underwater is what it does. So with technical diving, we have to also remove the nitrogen from the air that we're breathing to remove the narcotic effect. So the one inert gas that we can add back into it is helium. So helium is just an inert gas. It's stored in our system just like nitrogen is, but it doesn't have the narcotic effect. So when we do really deep diving, there's 3 gas mixtures that we use, which is oxygen, nitrogen, and helium. Those are the 3 mixes that we use for the air that we are breathing. And then it gets very technical, which is why it's called technical diving. There's a ton of math involved to make sure all of those figures are correct for the depth that you are in. So that's way beyond recreational diving.
Can you tell the story of how they came up with the dive chart?
The dive chart was invented actually by the Navy. And the Navy has, and what they are really good for, is volunteers. So what happened is, this was back in the, probably the early 1930s.
Daddy, we get dinosaurs?
You want to play with dinosaurs? When I'm done, okay?
Okay.
So, how the dive tables came about is the Navy had a theory that the nitrogen in our system was having an effect on divers, because they started diving way before that. Well, what would happen is they would just throw divers in the water, you know, with the old hard helmets that you see on TV with the one window in the front. They'd throw divers in the water, they'd let them go down and do their job, whatever that was, and then they'd pull them out of the water, and they had all these symptoms of decompression sickness, which they didn't know what it was. But they had a theory that the nitrogen had some play in the problems that they were having. So what they did is they did a study, and they just took, it was like 25 volunteers, and they put all of them in the water at the same time, at the same depth. And then they started pulling them out of the water after a certain amount of times. And they said, okay, we're going to pull the first guy out after 5 minutes. The second guy's going to come out after 6 or 7 minutes. And they went all the way down the line until they found somebody with decompression sickness. And then they would do it all over again for a deeper depth. Once they had these two depths in play, say 30 feet and 90 feet, then they could extrapolate, just by math, they could extrapolate all the different depths that came into play for this. And that's how the dive tables came about. And it's been refined quite a bit since then, but the Navy literally put divers in the water, let them get decompression sickness, and pulled them out one at a time until they found that time that you could not stay beyond that depth. And that's how the dive tables came about. The U.S. Navy figured those out probably in the 1930s, somewhere in that ballpark.
Guys, that's essentially module 2. You collect data, you look at the data and try to figure out a pattern. From the pattern, they were able to generate equations. From the equations, what do? They make the table.
Yep, absolutely. And they do refine them once in a while. As new data comes out, it gets more precise. It does change from year to year. It does change a little bit. Now, this is becoming old school already. Because now, instead of a dive table, what do we have? We have a dive computer. So a dive computer will figure all of this out for you. Literally, all you do is you turn it on, you jump in the water, and it calculates everything that you do. The advantage that we have with a dive computer is that it is more accurate than the dive tables. The reason why is here we calculate for every 10 feet of water that we're in. But what if we're not at 80 feet? What if we're only at 79 feet, or 78 feet, or 75 feet? You're losing time that you could spend underwater because you have to round up to the next greatest number. So if we did a dive to 73 feet, we would calculate that as an 80-foot dive. But we're really not at 80 feet, we're only at 73 feet. So we're really losing time that we could spend underwater. Dive computers calculate for every 12 inches of water that you're in. Dive computers know whether it's fresh water or whether it's seawater. There's a difference in both because seawater has a higher density, higher saline solution in it, so it has more weight in the water, and it's calculated differently. So dive computers are very nice. They calculate your surface interval, your second, your third, your fourth dive, everything that you need to do. The one big problem with a dive computer is what do you do if it fails when you are underwater? This is the reason why we still study the dive tables. Because if my dive computer failed on me right now, I would head to the surface, get out of the water, figure out what my table was for that dive, and then for the rest of the day you would have to do your dive table manually. So, dive tables are good and bad as long as you know the actual the table. We can always compensate for a failed dive computer. And I have seen dive computers fail. I've had several fail on me. I had one that imploded when I was underwater, and then I've had others that just leak, and I've had others that just turned off. They do get better, and they do get more reliable every single year, but it is a piece of electronics, so it can fail, especially when you put it in a water environment. Okay? Any questions on this at all? This is the main math that we do every single time that we do a scuba dive. Whether you're here, or whether you're in Lake Superior, or whether you're in Australia. Makes no difference in any way, shape, or form. Okay? Now the other thing that we are going to do with math while we scuba dive.
Taylor wants to ask a question. Do you want me to ask it for you? Yeah. Taylor wants to know if you've ever been diving with someone who's gotten decompression sickness.
I have.
Not me. Summer.
Yeah, what?
Go sit down.
You
We're
would
almost
be.
done, okay? Just gotta reach your phone.
You would be.
I have been in the water with people that have decompression sickness. Sometimes you will know right away that you get decompression sickness, and sometimes you won't know right away that you get it.
How long do you think, how long does it like take, like for you to like?
You could know instantly when you get out of the water that something is wrong, or it could be 12 hours later before you get it. So it depends on, number one, how big those bubbles are, how much blood flow they're actually cutting off. That tells you really how long it's going to take for the decompression sickness to set in. So it could be right away. The person that I was diving with knew instantaneously that they had it, and we were in the middle of the South Pacific. So there's not much around there, and I think they actually flew him to Australia was the closest one. So, right? Am I doing good? Good job. You want to
So
stand with
remember
me?
what you have, David.
You have M&Ms. I love M&Ms.
Daddy?
So yes, you can get it anywhere at any time. Doesn't make any difference who you are or what dive you're on. All right, the other way that we really need to calculate time, where it becomes very important, which is our airflow, no touching the board, okay? Awesome. Is shipwreck diving. Here we have one of the greatest things about where we live is we have the best shipwreck diving in the world. There is not any better shipwreck diving around the world than what we have. Lake Superior and the Great Lakes are one of the greatest shipwreck diving environments, and people come from all over the world to dive the Great Lakes. The reason why is the shipwrecks that go down in Lake Superior or any of the Great Lakes, they don't change because there is nothing in the water to change the wreck itself. They slowly decay and they slowly rust, but we're talking more than centuries that these have been in the water, and they look like they've been down there about a week. So this one is called the Chester A. Congdon. This one sank in Lake Superior. This is the biggest wreck on Isle Royale in the northern part of the lake. This was a freighter, a standard freighter, yes.
Have you seen the Fitzgerald?
I have not. Fitzgerald's in about 530 feet of water.
Oh.
So that one is a little deeper for most divers. There have been some open scuba divers on the Edmund Fitzgerald, but it's pretty rare. The technical diving that goes into a dive to 500 feet is astronomical. And it's not just the dive that you do, but it's your surface support for everybody that has to help you out with that dive.
And what's the suit that, you need a special suit, right? What are the,
You do
what
not.
are they called? What are the
You do
special
not.
suits
You
that
can
we
dive it
need?
on open circuit scuba diving.
What are the suits what I'm
A
thinking
nude
of?
suit is the one you're thinking
A
of.
nude suit, yeah, how much do those cost?
They range at probably about $75,000 to $80,000.
Jeez.
Whoa.
Yeah,
That's fine.
for a used one probably. So this is the Chester Congdon. This is a unique wreck for the one fact that this is a bow wheeler. So this is the bridge of the ship. This is where all the controls were. This is the ship's wheel. Everything is right here inside the ship. This is the only one on Lake Superior that is diveable that has an intact bow on it like this. What happened is the Chester Congdon in the middle of the fog in 1906, I believe, ran